There you go. Good evening, everyone. Celso Batalha, Astro 10, Evergreen Valley College. I have Charles and I have Tondo. Good to have you guys. So let's go to chapter 22. Before I start with chapter 22, this was not supposed to be showing. Um, see what are the required activities. All right, almost there. Too many clicks. And we are right here, 1718 stellar evolution. So now this chapter 22, we are focusing on the process that happens with the star once they reach the main sequence. And mandatory assessments, we have homework. Okay? And we also have a discussion that was initiated yesterday that has to do with stars that happen to be in a location in the Hertzsprung-Russell diagram, which is the key component in these 3 days of stellar evolution. So Monday, Tuesday, and Wednesday. In fact, on Thursday also we are dealing with the death of stars. Um, so in one particular location of the Hertzsprung-Russell diagram, there are stars that, for all purposes, we don't know exactly if they are contracting to be a main sequence. In other words, they are young stars, they are still in the process of being formed, or if they are an advanced, as far as evolution is concerned, star that has finalized its evolution in the main sequence and now happen to be expanding towards its demise. So the discussion is what are the conditions and what should you do to determine characteristics of that star. So how can you identify if the star is a young star or is an old star? So I do recommend that a better understanding of Hertzsprung-Russell diagrams can be um, very helpful if we use the simulation that is given in Nebraska Applets. And in particular, this one that I discussed yesterday, and I will talk about, and I will use again today. So some of the images of today's class can be seen here. So stars are made of gas. Stars don't have solid part. It's a gas that is very hot, therefore is ionized. So stars, they are formed out of gas and dust that happen to exist in a galaxy. And then two major processes happen to yield a star system. One process is called gravitational contraction. So depending on the conditions in the gas, gravity can be sufficient to initiate a pull of the star towards the central part. So this slow contraction that is followed by an increase in temperature all over the star happens when this contraction takes place. Um, as most of the gas happen to be concentrated in the core of the star, in the central part of the star, that region therefore, will be the one hotter. So if you take a star information, so let's say you have a spaceship and you travel, and now you face um, a few astronomical unity from a star information. So that star appears, larger than its main sequence counterpart would look like, and it's taking a slow contraction in it. Okay? Of course, we can't see the contraction going on. This contraction to be finalized take millions of years, depending on the mass of the star. But in addition to this contraction, this radial contraction, like a railing towards the central part, there is a second component, and that is the rotation of the initial gas that formed the star. And physicists and astronomers call that angular momentum. So this angular momentum, this initial angular momentum that exists in the nebula itself that gave rise to the star, as the star contracts, the star altogether rotates faster. Its angular velocity keeps increasing as the volume decreases. In addition to this fact, gas that is still pouring onto the star prefers to fall towards the disk, and from the disk it spirals and follows towards the stars, towards the central star. So what is the hallmark of a young star? Is one that has a contracting pre-main sequence star surrounded by a circumstellar disk, and out of this circumstellar disk, planets, satellites, and asteroids, comets will be formed. Okay. Now, the star goes through its evolutionary steps, and we will illustrate this now. And then eventually stars die out. And when the stars die out, they return material to the interstellar medium that is enriched by atoms these stars have produced. So you could say that the main role of a star in the evolutionary scheme of our universe is to be producers of building blocks of nature, be producers of atoms. So this is a typical profile of a main sequence. Stellar envelope with a hydrogen burning core. When we studied the sun, we saw that the solar core was the region, the volume, where thermonuclear reactions were taking place. So the core of a star, which is illustrated in this figure A, the core is the region where fusion reactions are taking place. So if you think about the energy that supplied the star with enough conditions for the star to brighten for a very long amount of time, that energy comes not from contraction, not from burning coal, but comes from nuclear reactions. In fact, it's a fusion reactions in which lighter elements are fused together, producing heavier atoms, and as a byproduct, energy is released. Now, what happened when the hydrogen in the core, which is illustrated in figure A, what happened when the hydrogen in the core is exhausted? That's the point of chapter 22. What happened when the energy supply of the star, what happened when the fusion reactions is gone? So what's happened is the core becomes depleted of hydrogen because it's all used up. The ashes of these fusion reactions, which is helium, is here illustrated with a purple or bluish coloration. In it, there is no fusion reactions because helium require a much higher density and temperature than the star has once this hydrogen is depleted. But So the helium core is called inert. So it's not active, it's not in fusion reactions. But this core is now withstanding the weight of the entire star, and because of that, this core slowly contracts. And as this core slowly contracts, it heats up, its temperature grows up. It goes from 20 million Kelvin, also when in the olden days of fusion reactions, and slowly keep rising to the point that eventually fusion reactions will take place. Now, surrounding the core, which is illustrated in figure B by this orange hydrogen burning shell, the hydrogen that surround the core, that was once part of the stellar envelope, this hydrogen start fusing. And the fusion of hydrogen there releases energy. Now, the energy that comes out of this system, core plus hydrogen burning shell, is sufficient to overcome and to overpower the energy star released previously when in the main sequence. And that energy is sufficient to initiate a slow expansion of the outer shells of the star. So looking the big picture here, the core of the star, once the hydrogen is depleted, the core of the star slowly contracts and heats up. The outer shell, because of this higher production of energy in the core, the outer shell expands and cools down. Now, the external gas, as it cools down, the collision among molecules diminish. And because there is less collision, the temperature falls and the star becomes red. So a byproduct of stellar evolution is a contracting core that heats up and an expanding outer shell that cools down. The two things happen at the same time, and it's harder for some students to conceive that. How come the core is contracting and heats up, and the outer shell is expanding and cools down? Yeah, that's the result of the balancing of energy that goes on when a star is about to find its evolutionary end. Here, example of stars in their different stage or evolutionary stage. So for all purposes, when you observe stars with your telescope or maybe using photometry, you can pin down the stars by their surface temperature, but you don't know their size. But their size can be told by gravity. So if they are expanded, their gravity tends to be less than it is on a main sequence, and less gravity in the star implies that some of spectroscopy spectroscopical feature tends to be of a narrow lines instead of a more broadened, as we would see in a main sequence. But the picture here depicts rendered stars with different sizes, which indicates also different stages in their evolution. So this is a HR diagram, as the HR diagram for a star that has completed its main sequence phase. So let's recall that the main sequence phase is the phase that goes the longest in the star lifetime. Is the one the star stays the longest. Is the one in which the core of the star is undergoing fusion reactions. It takes the longest time for this phase to be completed. Again, once it's completed, the star will go from the image depicted in part A to the image depicted in part B, where an inert core of helium is surrounded by a shell of burning hydrogen, and the star expands. And that's what you're seeing in this picture right here. In this picture, all these tracks coming out in solid dark lines, leaving the main sequence, all these tracks indicates the steps after the main sequence of stars of different masses. So if you look at the lower end, the lower right-hand side end of the main sequence, the stars there are of a low mass. So they slowly expand and they go up to be a red giant, whereas the last and the toppest track you can see, star of 15 solar masses, as you can see. So these stars, they leave the main sequence and they become super giants, those super luminous, 10,000 times as luminous as the sun, and they span a range of surface temperature because they undergo different steps in their evolution. Now, in the 20th century, when the telescopes became more competitive and the technology improved, what astronomers did, they observed in detail stars members of star cluster. So what is a globular cluster? A globular cluster or a open cluster like Pleiades is a group of stars that happen to share a common origin. They came from the same gas that formed them. So you could say that stars in a globular cluster like Hercules or stars in an open cluster like Pleiades, they all came together, they all formed together at about the same time, and then you can term them as coeval. They have the same age. Now, less strongly, you can say that since they were formed from the same material, they might share similar metallicity, same chemical composition, as far as they are formed from the same bag. This might not be necessarily true because when a group of stars are formed, a small percentage of them happen to be of the high mass end, and those high mass stars evolved very fast. And once they evolve fast, they explode and they release metals and newly formed atoms in the gas that will still form a younger generation of stars in that cluster. And so the metallicity is not necessarily a common factor on all the stars, but it's something to pay attention. So when astronomers observe in detail the chemical composition and the temperature, the age, and everything else, luminosity of of several stars that belong to the same cluster, they can build what's called the HR diagram or the Hertzsprung-Russell diagram of one of these clusters. And here's an example. So we have a cluster, which is, I don't know which cluster, there is not a name, but what is being shown here is that if you look in the lower end of this HR diagram, those dots represent stars. There are still slowly contracting towards the main sequence. And remember the discussion that we have this week. So the stars, the dots that you see in the lower end, they are dots of stars that are still contracting towards the main sequence. Now, if you look towards the middle of the main sequence and above, you have a bunch of stars that are already in the main sequence. They are already there. And if you look at the isolated member in the very top, it is already a supergiant. It is not in the main sequence anymore. So if you assume that all these dots represent stars of same age, In the lower end, and I will repeat, if you assume that all the stars that are represented in this diagram by dots, they have the same age, stars in the lower end, they are as young as it is the star in the middle of this diagram that happens to be the main sequence, and the stars in the very top, or one star in the very top. So they have the same age, but their evolutionary phase is different. The one in the very far, the lower right-hand side, they are pre-main sequence. The one in the middle, they are main sequence. And the one up there, they are supergiants. So although they have the same age, they are at different stages in their evolutionary path. So what makes them different? So what makes them different is mass. And with this, my friends, I introduce mass, the amount of content the stars has, as the dominant factor in stellar evolution. So stars that are low mass, they evolve very slowly. The stars of intermediate mass, they evolve slightly faster. And the stars that are of high mass, like O stars or like B stars, as we saw before, they evolve very fast. So they become main sequence quickly. In no time, they go through all their evolutionary burning phases in the central part of the stars, in their very core, and eventually they die. So their evolutionary is much faster than those of a low mass star. Here's another example. So in this cluster, the middle of this cluster, you have some main sequence stars. Most of them are pre-main sequence in the lower end that also represent the low mass members, and the isolated dot of a luminosity between 1,000 and 10,000 solar mass is already leaving the main sequence. Look at this HR diagram. So there are no pre-main sequence. Well, probably one pre-main sequence, the last dot in the lower part, right-hand side. So it's one pre-main sequence is still going, but most of the stars are main sequence, and the higher end is already out, right? Is already going out to become a giant star. So when they study this cluster, observe this point that is called the turn-off point when they leave the main sequence, when the group of stars are leaving the main sequence. So if we assume that all the stars in a cluster, they are of same age, and if we make an HR diagram for that cluster, and we determine the point in which the stars are veering, are leaving the main sequence, we can also, with the aid of models of stellar evolution, we create models of stars of certain chemical composition that resemble the star. We apply the laws of thermodynamics, the laws of gas behavior that we know. We include the rotation, we include opacity, and then we can determine how long those nuclear reactions in the core will be sustained, and then we can determine how old a star of a certain mass can exist. So in other words, these diagrams can help us to better constrain models of stellar evolution. So looking at this HR diagram, we can tell this cluster is 4.24 billion years old because the stars that are in the verge of leaving the main sequence, in the turning off point, they are stars typically that evolve as main sequence for 4.24 billion years. And then another HR diagram, we have the turn off point at about luminosity 1. And here is inset showing what is the inside of a low mass star like our sun. So in the very central part of the star, if we could see the layers as is being seen here, it would show an hydrogen shell fusion that it is surrounding a helium core that surrounds a helium gas infusion reactions that is surrounding an inert carbon-oxygen core. For a low mass star, the chapter is that as a main sequence, hydrogen is being converted into helium and energy is being released. Good. But then the hydrogen in the core is completely depleted. The fuel of the star is gone. And now the core is a helium core surrounded by a hydrogen fusion shell. The star expands, the core contracts. So eventually, this helium in the core that is inert will initiate fusion reactions. And when fusion reactions are initiated, carbon or helium is fused into carbon and oxygen. And those are the byproducts of helium fusion reactions. So the star again remains somewhat stable in the HR diagram because the core of the star is undergoing fusion reactions. Not hydrogen and helium, but helium and carbon and oxygen. But what's going to happen eventually? Eventually, this helium in the core will be depleted and the core will be a carbon-oxygen core, which is here represented in purple color. Now, when this happens, again, the core star heats up and contracts under the weight of the star, so the carbon-oxygen core contracts, the outer shells goes into more fusion, so you have a helium fusion shell on top of this core, you have a hydrogen shell fusion going on the top of everything, like a blanket thing. And this excess of energy that comes from these different shell fusion layers forces the star into an expansion mode called the asymptotic giant branch. So the star expands to become 10 to 100 times as big as our sun, and eventually all of that is expelled following reactions or energetics that are very much active in the core. And then the star loses all this outer shell, freshly formed atoms goes in the interstellar medium to form new baby stars, whereas the core is revealed. So this core has a name when it's revealed, and the name is a white dwarf. So a planetary nebula is one of the most magnificent and beautiful objects that are out there in space. Of course, all these colors are put in there to highlight features, but a planetary nebula is a phase in the evolution of a low mass star when the outer shell is expanding and the central part of it lies a white dwarf. So if you look at pictures of planetary nebula in general, let's see if I can find some. So see the white dwarf with an expanding gas, a white dwarf with an expanding gas, a white dwarf with an expanding gas. Same thing here, there, everywhere. See? So planetary nebula is this expanding gas that is surrounding a white dwarf. And white dwarf is a compact core made of carbon and oxygen, basically. Okay. And in high mass star, it doesn't stop in carbon and oxygen because the stars have enough mass to initiate or ignite the fusion of carbon and oxygen into neon, silicon, and heavier atoms. And the end of evolutionary end of a star, such as a high mass star, is not a planetary nebula and a white dwarf, but is an explosive event named supernova, yield a neutron star, which can be further lead to an explosive. Um, if it's part of a system, as you have material falling on it, it might lead to a white black hole. So those are the points I would like to show today. Um, there is some extra credit closing today, I think, so don't forget to check them. And any question? Charles, is you there? Okay. Good night. Hello? Hello? Hello?